Okay, so in this video we're going to be developing spherical coordinates, and we will use that to solve a rather complicated triple integral that we wouldn't be able to solve in Cartesian coordinates. So the first thing we need to do is we need to define what spherical coordinates are. So let's draw a little sphere here of radius 1. So that's just going to be the two hemispheres. So this is Z, this is X, and this is Y. So let's call the radius of the sphere rho. So that's just the Greek letter rho. And we should see that the relationship between rho and the other three coordinates is going to be the following: x squared plus y squared plus z squared. So basically this is just showing in parallel to the fact that if we take the radius of a circular region on the xy plane, we would get x squared plus y squared. And in general, the radius of any sphere in higher dimensions, so that any sphere in 4 space or 5 space or any other space higher than 3 dimensions, we would call a hypersphere. It would have a similar relation like this. So basically this we just keep going along with by adding more terms that are squared. And this is just a basic result from the distance formula. So we know that the distance between 2 points is going to be related to the square sum of those points or those coordinates. So now that we have that, let's try to define parametric equations for x, y, and z in terms of those spherical coordinates that we will develop. So the first thing we need to do is we're going to establish some point. So I'm just going to draw this in a different color just so that you can see it more clearly. We're going to have some point. Let's call this point A. And basically this point is just going to go from 0 to whatever point on that surface. So the length of this is just going to be the radius rho. And now this is going to have a projection on the xy plane, which is going to be the horizontal component of that. So if we have some angle here, then that's just going to be the cosine term of that total length rho. And then this is just going to be the projection onto the y-axis, onto the z-axis, and that's going to be related to the sine. So let's start by defining a change. So a rotation with respect to the z-axis, and let's call this angle theta. So the angle is going to be taken from the x-axis, but the rotation is really just with respect to the z-axis. So that's going to be theta. Now obviously to find this length, we need to find the projection that this rho, or that this radius of the sphere, makes with that. So in order to find that, we need to define another angle with respect to the z-axis. So let's call that other angle, let's call it phi. Okay, so hopefully this is not too confusing. Hopefully you can see that there is some logic to the way that we're defining those rotations, because we want all the angles to go from a positive axis. So in the case of phi, we're defining an angle that goes in with respect to the z-axis. So it's gonna go like this. And what this basically means is that now we're going to have the length, or this length rather, is going to be a projection here. So if the angle is sustained with respect to the z-axis here, then this total length is going to be defined by rho times sine of phi. So this is essentially the length of this little dotted line here. So this is going to be technically the radius that corresponds to that position of the point A along the surface of the sphere there. It doesn't have to be along the surface, it could be along any point contained within that spherical region. So now what we want to do is we want to express both x and y in terms of this. So if this is the radius now on the or the radius projection on the xy plane, then that means that we need to multiply this by some rotation here. So x is going to be the projection of this quantity with respect to the x-axis, which is going to be the cosine of theta. So this is a little bit complicated here. You will see that rho sine of phi times cosine of theta, and hopefully if you try to work this out very slowly, it kind of makes sense. We have this sort of quasi radius here, or this length, and we're taking it and we're projecting it on the x-axis, and by doing that we're basically multiplying by cosine of theta, so that gives us that. Similarly, if we want to relate y to this quantity and some angle theta, we can take the following. We're going to take the same quantity, sine theta. And why do we do this? Well, basically this is the same as saying that our radius is going to be equal to this. So if you remember from polar coordinates, all we did was x equals to r cosine theta and then y equals to r sine theta. So this is kind of the same thing. The only difference is that now this radius is dependent upon two other variables. The first one is the radius of the sphere, and the second one is this new angle phi, which is sustained with respect to the z-axis. And now for the z coordinate, what we're going to do is we're going to see what projection of this is. So we have the radius rho, and now the projection is going to be the cosine of that angle phi. So our z, our parametrization for z is simply going to be this cosine of phi. So this looks rather complicated, but hopefully you can see that this is all done by simply selecting an arbitrary point within that spherical region and then simply using trigonometry to derive those expressions there. So it should be straightforward if you work through the steps very slowly. Now the next thing obviously we need to establish is the volume element that is going to correspond to spherical coordinates. So there are two ways of doing that. We can either use a Jacobian by basically taking a determinant of a 3×3 matrix that results from the differentiating each of these quantities with respect to each of those variables here, and then just finding the kernel of that. But instead of doing that, let's do a geometrical derivation, which hopefully will give you a better idea of what's happening. This will give you better intuition. So what we're going to do now is we're going to take a surface area element. I'm going to call this surface area element ds for surface. And now basically this is going to be projected from the origin of the sphere. But obviously this we want a volume element, so this is going to have some depth to it. So it's going to be like a little cube that has been twisted, or rather just projected onto that surface. So we know that this angle is still sorry, not the angle, but the actual distance here is going to be rho. That's the radius of the sphere, which means that this little depth, or the change in depth, should be given by the rho. So that's the infinitesimal change along the direction of rho. So that's going to be the depth. So in general, the volume element is just going to be the surface area element times this little depth. So that's just going to be the rho. So now what we need to do is we need to find that specific surface element by using similar derivation as the ones we use here for the spherical coordinates and the parametrizations. So to do that, what we're going to do is we're going to zoom into this. So I'm going to draw a very big surface area element here. So let's suppose that we have some axis there, and we have this spherical kind of region here. So first thing we need is we need the width along this direction. So if this is the xy plane, this is going to be the width caused by a rotation with respect to the z-axis, like this. So we know that the distance from the origin, or the center of the sphere, to this point here that is causing the rotation, we know that the length of this is going to be rho sine of phi. So that's something that we already derived. So that's going to be the distance there, or the radius. And now we're going to rotate this by an amount theta. But now basically this rotation here is just an infinitesimal rotation d theta. And then that's going to correspond to the distance here, which is rho sine of phi. So this is going to be the width like that. And what is going to be here, because remember that this is just the arc length in that direction. Now this quantity here is going to be the arc length with respect to a rotation about both the x and y directions, or rather with respect to an angle subtended with the z-axis. So first thing we need to notice is this rotation here is happening with respect to the angle phi, so this is going to be an infinitesimal rotation or infinitesimal change in angle phi. And now the distance with respect to that is just going to be the radius of the sphere, because if we draw a little two-dimensional projection here, the distance is going to be rho. So this is just going to be times rho. So now all we need to do to find the surface area element is to multiply these two quantities together, and then we're going to multiply by this. So in the end, we're going to end up with the following. Element of volume is going to be equal to rho squared sine of phi, and then we're going to have d rho, d phi, and d theta. So this is going to be our volume element in spherical coordinates. Now the final thing that we need to establish is what are the limits, because remember that rotations are only valid as long as we complete one full revolution. So for theta, we know that this is just the rotation with respect to the z-axis. That's just should go from 0 to 2 pi. So those are the limits. Any angles that we choose between 0 and 2 pi are going to be valid. But now what's going to happen with the angle phi? Should it be 0 to 2 pi as well? No, it should actually be with respect 0 to pi. And the reason for that is that if you take, let's say this is x, y, and z. Let's say you take a semicircle, and this is just an area here. So basically, if you rotate this about the z-axis, what you're doing is you're making a volume out of this area. So this is just going to create a volume, which is going to be the volume of the sphere. So that's going to be a complete volume, because basically what you took was you took phi from 0 to pi, which cover two quadrants with respect to the z-axis. What happens if instead of going from 0 to pi on phi, you go from 0 to 2 pi? What's going to end up happening is you're going to have this full four quadrants with respect to the z-axis, and if you rotate it by 2 pi along the xy plane or with respect to the z-axis, you're going to get a double volume, because each of these semicircles is going to cover the same amount of volume. So it would actually not be the proper definition. So that's why we have this. And finally, rho is going to go from whatever radius we define here from A to B. So that's just going to be defined by the problem. So hopefully this wasn't too complicated. Hopefully you can see that this can all be derived from simple geometry and trigonometric relations. And in the next video, we will actually go into solving triple integrals involving these spherical coordinates.